Okay, hello again. Is my voice clear?
Yep, we can hear you well.
Okay, thanks. So first, thanks for being here. Yeah, thanks for the confirmation that that's a spirit that's needed indeed. We need to shout out for one another in the chat and so on and keep up the good enthusiasm and momentum. So welcome again to the second session. We are going to talk about the quantum AI and the quantum technologies. Why do we need quantum computing? I'm going to use two different set of sources. And these two different sets are going to highlight part of the applications and the part of the use cases and also the quantum hardware. First, I would like to mention that we started the journey also together with pioneers from Egypt and Dr. Ahmed Shawi Moussa, where he also gave a presentation at Alexandria Quantum Hackathon last September. And this hackathon was one of its kind about the quantum technologies and also have a way to support the students and the momentum in quantum computing in general in Egypt. So that was nice. A lot of people have taken this opportunity, and that paved the way for some of the hackathon participants to have scholarships, internships, travel grants, and also start international collaborations and so on. Recently, Alain Chancey, my co-founder of MolKet SAS, and I were co-guests at one of the podcasts in Emirates, hosted by Malak Tarabulsi and John Barnes. And this podcast was about, okay, what now we can use from quantum mechanics, quantum computing, and of course, untangle some of the hype around it and discuss the roadmap of the technology. So feel free to revisit this podcast if you'd like to hear more about the industrial side of the technology and the struggle of companies, how to disentangle the hype from reality, and how to genuinely judge about when you read an article about quantum computing, is it really a genuine application, and what kind of things we can do with genuine applications from quantum computing. Now I'm going to start with MolKet. So MolKet, we started MolKet as a startup for quantum software and also consultation. So it offers services around the quantum AI. It's now based in Paris. And in MolKet, we are really producing software, mostly open source, for the majority of it to test about the industry and so on. And of course, pave the way for applications, especially in chemistry and the chemistry-based algorithms. And of course, we have iQafé. iQafé is sort of an educational arm where we organize and help in organizing hackathons and seminars, labs, conferences, educational tracks around the world. And we had extensive collaboration in Egypt where we organized several quantum AI labs. And now we are happy to take this opportunity together with Cairo University to help and contribute in this brilliant spring school in quantum technologies that aim to build the community. And now we come from the community. The community is about quantum computing. And the question will start, why do we need quantum computers and what quantum computers can offer for us? And if we know this, can we know a bit about quantum business and software and quantum AI and a bit of quantum education? So those are good questions. And this is a slide for MolKet. I was just gonna show it before we step into the technical details. So in MolKet, we propose and leveraging AI to accelerate chemical design and the quantum dynamical simulations and leveraging different technologies from quantum AI. Feel free also to test our open source simulator, which is also dedicatedly designed for chemistry. You will find all the details on MolKet GitHub repo and website. Okay, now we see the boom that happens in AI in general. So we have several architectures and AI architectures around the world. AI is more mature now. We see all of these nice applications from Gemini, ChatGPT, Watson X, DeepSeek, and many Claude, and many more. So we see all of these nice applications, and the question become now, we see now AI as a mature technology. How about quantum computing in general? So the AI has already specialized models. You can download them. There is a lot of open source models you can download from the internet. You can test them on variety of use cases and get much more in generating videos, even finding bugs. I mean, there were bugs that were not found for many, many years, or like almost for 25 years or so, for in like a Git or anything. And thanks to LLM-based architectures, those bugs were found. So when we come to AI, the difference become, why do we need quantum AI in general? So I started in the PhD working in quantum molecular dynamics for James Webb Space Telescope. And there was a problem of simulations. We needed to simulate small molecules to have data for molecular astronomers. Those data can contribute to establishing a model about the chemical evolutions of these interstellar media. However, we use quantum mechanics to make or enable those simulations. And in quantum mechanics, we have to predict the presence or the amount of these molecular species in interstellar media. To obtain a spectra or the fingerprint of these molecular species, NASA, in collaboration with ESA and also other space agencies around the world, they have launched a very powerful telescope called James Webb Space Telescope. And the James Webb Space Telescope indeed has a powerful near and mid-infrared observational capabilities. And thanks to that, they can observe with these advanced cameras very nice high-resolution spectra. So the spectra sort of something that you receive like this with energies and intensities. And then you need to assign each peak of this to the molecular species that correspond to. So there is some energy transition that would emit that light. And for that, we need powerful quantum mechanical simulations, and those are very expensive. Hence, the simulations with quantum chemistry or quantum molecular dynamics, the molecular dynamics in general, these are very expensive computations. We are going to see this use case in the third day when we dive deep into quantum computing for chemistry. But this is just an overview that we have the computational complexity, and this is what pushed some scientists like Richard Feynman and others to think about, what if we can simulate quantum systems by other quantum systems? And that simulations would mean that, can you leverage the way that the quantum mechanics work to enable computations, and this computation can simulate another quantum system, and then you don't have a classical system at all. You can get rid of this classical complexity and sort of reduces classical complexity and get something that grows linear or in a very steady way. So the computational time doesn't scream or becoming infinite. No, you still have it tedious, so you can still go and simulate much larger systems as well. Of course, this we are gonna see during the presentation on the third day. However, the take-home message here is that we have computational complexity of, in particular for molecular simulations, for example, and those are very important, because if you want to make a simulation that is very accurate, you need very good level of theory and, of course, a very good computational model. And good computational models would require a very large amount of equations to solve, and hence we have this hurdle of computational complexity. And this is why quantum computing came into play. And the difference, as Dr. Ahmed has highlighted in the first presentation, between the qubit and the classical bit is that the qubit, which is a unit of quantum information, can exist in a superposition of states. It can be in 0 and 1. It doesn't mean it lives like this forever in 0 or 1. No, the qubit is like a classical bit. So the classical bit, you have 0 and 1. That's, of course, normal. The qubit can be in 0. However, if you would like the qubit to be in 1, you need to do an operation. So the default state for the qubit, if it is 0, you need to do an operation to make it 1. And it won't last in 1 forever. So it has a certain lifetime. This is the first difference between both cases. The second thing, you have the ability or some magical way to project this qubit to be in a superposition or a combination of two situations. The superposition here is different from the classical superposition. They are not added up to one another. So you cannot have two waves and then you calculate the maximum amplitude that comes from both of them. No, you have two situations that are probable at the same time related to the coefficients next to these situations. So for example, if this is, for example, 1 over root square of 2, this 1 over root square of 2, if we square, then the probability to be in 0 is 50%, the probability to be in 1 is 50%. When we do the measurement, only one situation will survive. So imagine you have two default routines in your life. Either you are eating or you are sleeping. Then if someone doesn't enter your room, you could be like sleeping or eating. So there is 50-50 chance of you to be sleeping or eating. However, when someone enters your room and opens the door, you will be found in one particular situation only. So that's a qubit. However, in quantum mechanics, this superposition is real. So it can be tested, it can be seen, it can be touched in many ways. So it's measurable. So it's not something that we work with statistically speaking. It does not exist. No, it exists, and there is a lot of measurable indications around it. What we see here now is a cinematic view of IBM quantum system, and that has announced in around 2019. And of course, this picture is nice because it shows, of course, it's cinematic, but it shows that you have a quantum computer, which looks nice, but if you unfold this one, you are gonna find huge system like this. This tiny dot here is a quantum processor. This tiny chip contains the number of the qubits or the qubits that you are gonna work on in your system. And all of this big system and plus the cryogenic stat or the cryostat, these are fridge to cool down all of these electronics that are used to control and operate the quantum chip. So the quantum chip does not operate around itself. It's like you have your own laptop. You need a motherboard with different components in order to handle the tasks that has been subcontracted to the processor. So you have all of these technologies. So the quantum computing is not only about the fabrication of the chip that has the qubits. No, it involves innovations in classical electronics as well. The electronics that are used to control and operate the qubits and also read the measurement as well. So it can load data, it can operate them, so it can execute certain quantum algorithm and also read the results. If we see a high-level way of how to perform computations on this, what we see here, we see these lovely qubits are on the left, and these qubits are manipulated in a certain way. This way reflects the algorithm that we would like to execute. So each algorithm would form a sequence of steps or operations that are translated into gates. These gates will impact and manipulate the state or the quantum state of the qubits to perform a computations. And then it's up to which part of the algorithm you need to measure. When you measure, you retrieve the information back. So the quantum system is like a black box. You load information, you can control them with all of these electronics, and then you retrieve the information back, convert them from quantum data to classical data in order to comprehend them. And this is done via the measurement. So this is a high level. There is a lot of applications, different theories to deal with, like, okay, can we have a weak coupling with the qubits to measure? But all of these are a nice dimensionality to look at the problem, but now we are seeing the high-level picture of this system. And hence, we see the quantum full stack. You have the quantum chip. On the top of it, you need to convert the quantum data into classical, and you have the microarchitecture, and then you have the instruction set architecture, which has the instruction that you would like to perform, and then you have the algorithmic runtime compiler, and then the programming paradigm and the Q algorithm. So if we work, you have your algorithm here, you need to write it in a certain programming language, like for example, Qiskit that we are gonna have a training on, and the Qiskit is an open source package or software development kit offered and provided by IBM Quantum. And then after that, you have a compiler. The compiler would translate your algorithm or the quantum circuit into a native gate set or the suitable layouts and operations for this particular hardware and optimize your system. And then you have the instruction set architecture, which goes to the microarchitecture in the microchips, and then, of course, go to the classical electronics, make operations on the quantum chip. And this full stack approach and high level understanding, it's applicable for many use cases like logistics, finance, portfolio optimization, quantum simulations, chemistry, battery design, and many more. Here we see an example. For example, if you have quantum chemistry or you have some data, some simulation you would like to do, you need to convert from the problems that you have into something that the qubits understand, and this is also forms some theoretical complexity to do so. So in a nutshell, how this is done on a quantum computer, you go in a certain approach. I'm gonna just switch now to the second set of slides. And here it comes. You need just to choose a single slide and get rid of this one. Okay, so hopefully now everything is clear. So how this is done, basically, we have an overview or a high-level approach to look at the quantum computer. All of quantum computers share the same. So why we are saying quantum computers, not a single, because there is different technologies to implement the quantum algorithms. They are not one or a single algorithm. They are different quantum architectures that are used to implement the quantum computer. So for example, we have the photonic quantum computer, and this means that you are using photons and lasers that are going within waveguides in a particular way to emulate and perform the quantum algorithm. You can have a different technology called the superconducting quantum processor, and this is similar to Google New Willow chip and also IBM quantum computers as well. And you can have another technology like ultra cold neutral atom quantum processor, and these are neutral atoms where the Rydberg states are controlled in a specific way, and then you can perform computations on them. There are several technologies are in development, like the cat qubits. We have heard, or maybe potentially you heard about the Amazon Web Services, a new Ocelot chip, and of course Microsoft Majorana 1, and this sort of a prototype toward enabling what's called topological qubits. And then we have the IonQ, which is the ion or trapped ion technologies. So we have different types of technologies. Around 9 to 12 are being realized. There are still many more still in R&D. But of course, this changes every day. There are companies working in stealth mode. So please feel free to update your knowledge all the time by reading the news about the quantum technologies, and of course trying to establish your own way of reading in order for you to verify the information that you are looking for. And of course, you can have certain things like you can have what Dr. Ahmed already showed in the first presentation. You can have something at your home, like a SpinQ quantum computer, and this one has 2 to 3 qubits. It might have more, but the technology that this quantum computer is leveraging is complicated, and also it's very hard to scale. So it's good for education, good for research, but of course, the technology of using the nuclear magnetic resonance might not be suitable for large use cases. where you need many more number of qubits. Of course, you can have a simulation on Raspberry Pi, or you can have something like this. And in MolKet, we already have technology similar to NVIDIA processor for training. You can also, there is also open source available quantum computer and portable technologies. You can check them, and those one are good for research as well, and good for students who are developing thesis or small simulations to try and compare the results with what they see actually in the lab. Okay, so how we project our thinking into the quantum computer? Typically, we need to prepare a problem with a classical algorithm, and then this problem is translated into a quantum algorithm or a hybrid classical quantum workflow. And then once this has happened, you need to think about how to initialize data. Do you need to initialize data? Do you need to have a predefined data for your system? So this data has to be loaded into the qubit system or the quantum register first. And then this is, you can translate your quantum algorithm into a quantum circuit and execute it, and then you perform the measurement. So if we go here, this is a flow chart that depict this picture. You have the problem preparation, you map to algorithm, and then you have the qubit encoding, and then you need to run a quantum circuit and perform the measurement. Each one of these steps we are gonna see in the labs. So I'm giving you high level overview, but during the future sessions, you are gonna dive deep into each part of these, from the problem preparation, how to define the problem, what's the kind of mapping you can use, the data loading, the execution, and the measurement, and the post-processing as well. When we come to the realization of the qubits, you have to be aware that the qubits are physical systems. So they are not something that you emulate the classical bit. You need to make a system that can mimic or emulate the quantum mechanical concepts. So for example, in quantum mechanics or the quantum world, we have many characteristics that distinguish the quantum world from the classical world. And these like the superposition. We don't see superposition in classical world. You are not gonna walk in the street and find people in superposition. Everything is predefined. You can use very simple equations from Newtonian mechanics to compute how car will go from one place to another, or how a bike will travel, or even how you can walk. However, when we dive deep in quantum system below a certain threshold related to Planck's constant, then things become fuzzy, where you can have a superposition. You don't have a specific position anymore. You have sort of probabilities, and you have combination of many situations that coexist together. That's the first thing. The second thing, you can have systems that can entangle. And the entanglement here would mean that you cannot describe one system independent from another if they are entangled, so they are correlated. And subsequently, if you do a measurement for part of one system, this measurement will impact the other one, even if they are far apart. So you can also have teleportation, you can have tunneling, many things you can do in quantum systems, which has those things have no equivalence in classical world. And for that, if you wanted to work on a qubit, you need to visualize or leverage the qubit presence. You need to leverage how the qubit is formed and make a qubit that can emulate a real physical system. But only you have one caveat. You need to be able to control this qubit. The qubit in principle is two energy level system. So it has two levels. You have a 0 or 1. So if I can just make a simple drawing. Then activate the pen. Yeah, that's a wrong color for the. So you have something like this. For some reason, the color does not activate. Okay, anyway. So you can have two ways of visualizing this. You can have two level systems. And those system would mean that you have a lower system and you have a higher state. And this would mean you need to have two energy level system at least to start a qubit. So you cannot start a qubit without having two distinguished energy levels. And the second thing, you need to be able to control them. So if you cannot control them, they are no useful for you. So you need to have a quantum bit, which is called qubit, and be able to control it. Since a qubit is a quantum system, you have two different types of systems in the universe. You can have a fermionic qubit or you can have bosonic qubit. The fermionic qubits is related to the types of particles. So people who study physics or coming from a scientific background, they usually can understand hardware simulations. And people coming from software engineering, they are good in applying use cases because they know how to optimize a quantum code, how to leverage it in applying for use cases and interpret the results. However, both of them are using the same architecture, so you need to be familiar with qubit type because it can impact the algorithm that you are running. If you have a question, please feel free to drop it in the chat. And once you have this, you need to use different types of math to convert or project your thinking into the quantum computer itself. Now I'm going to switch back to the original slides. Okay, so we now learn about this. We need two energy level system in order to be able to study the qubit. So we need something with two energy level system that we can use and we can apply. So if we cannot use that, then we are no longer having the technology. So we have like a ground state and excited state here. And these are the two technologies, or the two energy, these are the two distinct energy levels that we need. So the controlling the distance or the energy separation, it what gives me how I want to do operation. So if I have a superposition, it means that my system exists in both, partly with certain probabilities. If I have a system in 0, it will stay in 0. If I have system in 1, it will stay in 1. So if I have system here in 0, that will stay in 0. And if I have here system in 1, that will stay in 1. So we are going to learn about this tomorrow in the introduction to quantum computing. So in the introduction to quantum computing, we are going to see all of this in much more details. But now we just are viewing this is how the quantum computer is working and how the industry is progressing in the field. Okay, so is execution of quantum computers complicated? We hear the question this all the time. It is not. However, it requires to understand more about the physics and be able or fluent in the different applications that are offered. For example, now there is an open source paper. You can see a quantum engineer's guide to superconducting qubits. This paper is very nice because it offers to you full stack and the full view on the quantum hardware, how you can start a small quantum computer in the lab by just understanding all of the steps that are required. And by understanding this, it doesn't mean that you understand them theoretically, but also you can just try every step in the lab and try to reproduce the results yourself, compare with simulations and so on. Now, we have the quantum systems. The quantum systems have problems, which are like can be seen in a a very specific way. Those quantum systems are very sensitive to the interactions with the environment. This is why we need technologies to cool them down and to keep them in zero or sub-millikelvin. Not all technologies need this. However, most of the technologies need super cooling and super cooling calculations. Yes, we are gonna give small calculations tomorrow. So that's tomorrow. We are gonna start from the first presentation. We are gonna start with intro to quantum computing and introducing the gates and so on. But you need to get this idea from here in order to progress tomorrow in the session. Indeed, for some companies, I see a question here. The quantum computer science students have taken master and PhD in order to get into the field. It depends on the positions that you are applying for. Let us discuss this after the presentation because it's a very important question indeed. Now, what we see here, since the qubits are very sensitive to the interaction with environments, they can have errors. So the quantum system or the quantum things that are there in the quantum system can collapse and they can be destroyed, and we need to keep them alive for a very long time. And for that, we need to protect the hardware, shield it from the interactions, keep it at very low temperature in order to reduce the vibrations and the crosstalks that can happen between the different components in the quantum computer and so on. And on the top of that, once you can do everything right, you can have all of the innovations that you can have, you can still make an error correction, which means that you can perform certain operations to correct the potential errors that happened in the quantum systems, either on a hardware level or a software level. What we see here, we see an achievement where Google has announced recently, it's not really recently, it was late 2024, that Google's new Willow chip. And this Willow chip is a new processor, and the good thing about it, it has a new fabrication, so the quality of the qubits are better. And indeed, there are two chips working together. One performs the quantum computations and the other performs the error correction. So there is hardware error corrections that happen in real time. On the top of that, there is also software error or algorithmic error corrections that happens in the post-processing. So there are two components that are contributing to one another. And this here, what we see here is the logical qubit operation limits. We are going to touch or explain more in the upcoming sessions. But as a take-home message here, there are different codes where they can group the qubits in a different way. We have two types of qubits. We have what's called logical qubit, and we have what's called physical qubit. The logical qubits are the ones that we assume in the algorithms. Those are the perfect qubits. We think of them as a computer science way. If you have this qubit, you can perform X, Y, and Z of operations on it. However, when we come to the lab, we have the physical qubit. This is the one that actually exists in nature, and we could create in the lab or leverage in the lab. And those qubits are imperfect. So in that sense, you might, for one operation that would require one logical qubit, in order to make an error correction and to perform the operation, you might need to substitute or represent this logical qubit by many a number of physical qubits. Sometimes you can use 60 physical qubits to represent one logical qubits, and this ratio depends on the what we call it qubit fidelity and gate fidelities as well. We are going to touch upon that also in the upcoming session, but this is just a warm-up session for tomorrow and the upcoming days in the school. Here we see a depicted image. So if you have a physical qubit, those are the blue dots. Then the grouping of these is what gives the logical qubits as well. Okay, so now we arrive to this distinction. And of course, if we dive deep into the characteristics of Google Willow chip, we can find how this advanced the field. Of course, that was in late 2024. Now there were more chips coming from IBM and the major players, and also new startups that might have a better performance and have better metrics. So feel free to check them as well. During some of the panel sessions, we are gonna discuss them as well. Let's now also explore here China also produced a similar processor to the one that Google has already developed. And this one has 105 qubits. And indeed, what they have done, or what's remarkable, it has been published in the same sort of timeline. So they were close to one another in time. And Chinese processor had an extensive benchmarking and testing and a lot of tables. Of course, it's very hard to verify those numbers, but the team, as you see here, there is like almost very tens of names are have collaborated together in order to enable such device and also do the different tests and computations. So each company now has a roadmap, and those roadmaps have been updated. We are going to discuss them in real detail in upcoming. So Google has its own roadmap, IBM has its own roadmap, and so on. And those roadmaps reflects what this company envisioned for the technologies and also how they extrapolate or see the future with respect to the hardware that they have already in their premises. And for that, IBM is now expecting by 2029 we have a fault-tolerant quantum computer. It means that a computer that has a very large number of qubits that can enable useful computation. So you don't worry about the error anymore. Here we see in Google roadmap or things, we see here a sort of an industrial way to look at the quantum computer. So what types, let's just paraphrase it in that way, what types of computations or technologies do we have? We have different types of technologies to enable quantum computations. However, we can categorize them in two main technologies. There is also several other technologies, but in this slide we have two. We can have what's called the universal quantum computer, and we have the quantum annealers. The universal quantum computers, those are mostly gate-based. It means that you work with gates to enable the execution of your algorithm. So you construct a quantum circuit. This quantum circuit has a bunch of gates in it, and these bunch of gates are arranged in a specific sequence that emulates the algorithm that you would like to execute. When it comes to annealer, it's different because the annealer is using the characteristics of a physical system and the evolution of the system to find the answer for you. So you are trying to find a way where you can emulate or find a similarity or analogy between the system that you would like to study and the annealers. If you would like to optimize a thing, the annealers can find the ground state, and this ground state could be the optimal values that you are looking for in your optimization algorithm, for example. And for that, we can have different technologies. We have the hardware here, and in this hardware, we have the seek for the more general quantum computation, what's called the fault-tolerant, and of course the noisy, which we are having at the moment. You can also make simulations and also in your processor, and using these simulations to judge the quality of the quantum computer, and of course the quantum annealer. What is now available in the market? We have D-Wave quantum annealer, and this is claimed to be 5,000 qubits. We have now IBM and the Google and Rigetti, and these have different types of chips with different number of qubits. This is for the superconducting technologies, and for trapped ions, we can have from Quantinuum a chip about 56. Now they are much more. Of course, these slides I've prepared a few months ago. You might find the new chips that are being offered by Quantinuum and of course IonQ as well. And we have the ultra cold atoms, and we have Pascal and the Q era pioneered in that. So you see, it's not easy to judge about which technology is flying out. We have when we go to the quantum computer, we have what's called the universal quantum computer, and we have what we call the quantum annealers. And each one of these have different mechanism to work with. And of course, in the quantum or the universal quantum computers, we have several technologies like the superconducting, the trapped ions, and the ultra cold atoms. We have the photonic also, and we have many more. And each one of these technologies has its own advantage and disadvantage as well. However, what we have now, they are noisy systems. This is why it's called the NISQ era. And the goal is to achieve or develop a fault-tolerant quantum computer where it can use error corrections, and it has many number of huge number of qubits that can perform meaningful computations without the worrying about the errors that might happen. So it's like a classical computer, but many very small classical computer. If you understand the analogy, of course, it won't run the same algorithms, but it just emulates the developments that happen in 60s and 70s in such field. And here we see a figure about how these companies now are progressing in developing the number of qubits according to what they have in their roadmap and what they have actually realized. And we see, for example, IBM is doing fine. Pascal is the same. Q era, okay, that's nice. IonQ had a bit of dip, but of course it can catch up later, and so on. So William Slater already has shared a very nice post about the Moore's law, and of course the question becomes: do we have a Moore's law for quantum computing? And the answer to answer this, we need many inputs, like from the qubit lifetimes, the qubit fidelities, the physical qubits, and the logical qubits. And for these, we can see, okay, these are the trends we see here, the trends of the D wave, the number of qubits that they are developing in their annealer systems. And we see here the IBM quantum system, Rigetti, and Google. And of course, we have some trends. So, but can we establish a Morse law? Then that would require from us also to understand the development as a technology. Do we double really the number of the qubits every iteration or every development, and so on? Hence, Morse empirical law cannot be easily translated to an equivalent in quantum computing because it's still a developing technologies. There is a lot of innovations that happening, but they are happening at a different pace depending on the complexity in the technology that is utilized, and of course, not only the technology but the engineering system and the innovation in engineering to enable the electronics and the control and the error corrections around this specific technology. Now we see here the quantum advantage, and I would like to end this presentation with a quantum advantage. When we go to quantum computing, there is a dream for a quantum advantage, and the quantum advantage was perceived previously as something that remarkable will happen that will exceed what classical computers can do. Of course, everything you do now with a quantum computer pretty much mostly can be done on a classical in a much more efficient way because there is more knowledge. There is many ways to do things efficiently on classical computers. So this dreamy quantum advantage is not there. However, the quantum advantage is defined in the following. Either you can do computations in much faster than a classical computer, so you can use a quantum computer to perform much faster computations, or you can use a quantum computer to produce more accurate results in your model, or you can get a new knowledge about the type of algorithms that you are using. So you have three categories where it can show the quantum advantage. And here we see the particular use case and the time frame of each use case. We are going to see this in real time. And when we come to the fourth day, when we touch upon the cybersecurity, and here we see, for example, how much it would require from us to, for example, to break down RSA 20, 40, 48, and so on in 24 hours, and how many number of qubits we would like to have and the time frame. There was a recent estimate that you need, for example, about 100 years or 110 years in order with a good quality qubits to decrypt and crack RSA. So that's also one of the things to pay attention, that we are not there at a level where the quantum computers is a real threat, but there is huge development that's happening, and those numbers and those metrics are being updated all the time. Okay, now the expected market cap. The quantum computer is growing indeed, and there is a lot of companies that still predict that by 2030 we are gonna have huge market cap for quantum technologies and the quantum computing in general. And this is because of the expectations and roadmaps that have been put forward by companies. And this market cap would mean that, okay, this would reflect the size of commercial deals and the commercial products that are exchanged or based on services provided from quantum computers or cloud-based services as well. So there is still room to open startups there. However, the only challenge is to educate clients about the quantum computing and the quantum technologies and what they can benefit if they cannot benefit from it now, how they can use it in the future when more mature and the more ready quantum hardware is available, what they can do with it. Okay, so why Moore's law cannot be established? We have different metrics for that. Okay, that's fine. We are gonna discuss them later. And now the question is for you: what the quantum advantage really mean for you? And we defined now the quantum advantage as a way to um, like find the expected value from the quantum hardware, which could be faster algorithms or more accurate algorithms, or maybe a new knowledge that you can develop from the work with quantum computers when you think about new algorithms. So there is still no concrete definition of quantum advantage. It is developing based on the technology. However, in 2029 and 2030, expectations from major players that the quantum advantage would mean that you can really perform computations that you cannot do any equivalent operation or execution on a classical computer. With that, I would like to conclude the session. Bear in mind that this is an introduction only. So tomorrow and after tomorrow, in the third day of the school, the fourth day and the fifth day, we are going to discuss more technical details about this. So we are going to see this in more details. It's just the overview of the market and how the market proceeds in adapting with quantum technologies and the quantum computing in particular.
Thank you very much,
So,
Dr. Taha. Very interesting, very informative presentation. Indeed. We have some questions in the chat. Omar Hossanuddin is asking, do computer science students have to take a master's PhD in order to get into this field? I think this question was asked in my lecture, right? Or is it repeated? I remember it was.
yeah, maybe, yeah, some maybe a different person asked it also.
Okay, so we get into the following question, Mr. Ahmed Mohsen Rifai. Can you give a small conclusion for what we have taken till now to, inshallah, digest it well? Well, I don't know if Dr. Taha will have an answer to that. I
Yeah.
don't know. I think you get the titles of the lectures from the agenda. Maybe Dr. Taha has a better answer for that.
Yeah, thanks, Dr. Ahmed. I think it will be the same. You can get the titles indeed. And of course, you need to attend because it's a problem if you read the summary, it won't really compensate for the actual trainings that you can do by hand and also on your computer. So now you get an idea, you get a presentation of Dr. Ahmed, and you have now an extra presentation about the market and the overview about the technology. Then from tomorrow, be ready to dive deep into the technology itself and how to use the quantum algorithms.
Okay, there was one asking about the recording, I think, and the material. I think we will announce in the due time about that, where to find these things. But we have to finish all the lectures and do some editing and then let you know where they will be posted. A question from Ahmed Abdel Hamid. I have a question about the quantum noise. How can we be sure of the results when we are sure that even the quantum computers themselves what generate noise that can affect each other. There's a word here that I can't see, but the question is, I think the question means that regarding the error, how can we trust the calculations if we understand that the calculations are having intrinsic errors into them?
Yes, thanks, Dr. Ahmed, and thanks for Ahmed for the question. Indeed, we have a quantum noise, and we have the risk of having, of course, errors from quantum computers. And what error correction protocols actually do is that they try to make sure that you can spot this error. And one of these things, for example, if that you use a computation with 1 qubit, you share the information among 3 or 5 qubits, and then you use some sort of the protocol to predict for you which qubit had an error, and then you can perform a post correction for this qubit. So the error correction protocols have this sort of built-in correction mechanisms that can correct the errors that can happen from the quantum noise, and that can happen from a hardware side, like what we have seen in Willow chip, and from software side where you can execute a protocol and you can have a lookup table to perform these corrections.
Okay, thank you, Dr. Taha. I think there was also a problem early in the 40s or 50s about that with the classical computers, where IBM made an invention to fix the erroneous bits. So this is not exclusive for quantum computing.
Yeah, definitely, definitely the same. Now we don't feel it because we have the fault-tolerant classical computers, but indeed in quantum we have limited number of qubits. But when we have more, then we achieve this fault-tolerant, and then when we talk now, we encode the bit, for example, in the amplitude modulation in 16 bits, and then they are sort of protected. And then if we do the same with qubits, we don't feel this individual errors that might happen, but that would require these massive quantum computers and innovations in engineering to enable their presence.
Okay, here is a comment from Dr. Hisham El-Mahdi, wishing that we number the slides to take notes and use as reference when asking a question. Here is a question from William Slater. Quantum is the future of computing, and the people attending this course are the future of quantum. Good on all of you. Okay, so it's a comment. Thank you. Muhammad Amin, may I ask in talk or not? Yeah, I think we can allow you to unmute your microphone, but I don't know. Muhammad Amin.
Okay, doctor, can you hear me?
Okay, yeah.
Just due to some malfunctioning in my Gmail app, I missed most of the sessions, so I want to know what I have to do to summarize what I've missed and to know what is coming, because I don't know the system due to some malfunctioning, as I mentioned earlier. So I want to know what should I do. I know it's not about the content indeed, but I want to know the system so I can go on till the finish of the session or the school. And sorry for being long, but that is what I'm asking for.
What you mean by knowing the system? What system?
What is the system of the sessions? What is the tutor is gonna go? Cause I wanna know the system of teaching, the sources, the resources, and the stuff like that.
The lectures are given. You try to not miss anything, and the schedule is given. So if you want to know the titles of the lectures given and the sessions given, the schedule is announced. I feel, Dr. Taha, do you have a better answer than mine?
No, thanks, Dr. Ahmed. I think that's pretty much it. We have the schedule, and with the schedule we have all of these lectures, which indicates which one is plenary, which one will be tutorial and lab. And with the lab, you are gonna follow with the instructors the codes they are gonna show. You try to install some libraries and so on. They will gonna show you from scratch everything. So, please follow the schedule, and then you benefit from the hands-on. And the recording will be available later, as Dr. Ahmed said, but then we need to work on them to make them in a better shape.
But for today, it is just
the
an
short answer
introduction,
is
right?
the short answer is to try to miss anything, because there is no magic way of compensating a missing lecture by telling you something to not miss it. It is, you have to attend, do everything.
I didn't mean that. I meant that just for today, because I'm malfunctioning in the app. I just mean, what do I miss? I want to know, is it just an introduction for the field, for the quantum computing field as all, or do I miss something specific?
No, it is difficult to answer that. You have to make this judgment yourself. Okay, Abdullah Hisham is asking me to raise my voice. Apparently, there is a problem with my mic. I will try to fix it. I'm trying to get close to the mic now. I also will check the mic level to make sure microphone. Yeah, the setting is right. There is a chance. I will try to use an external microphone tomorrow to avoid this problem. Okay, let's see if there is something else. Why do we convert to classical computers when we are trying to solve a problem with quantum computers? Why not solve it, model it with a quantum computer end to end?
Yeah, so that's indeed a good question. Indeed, now what we it depends on the available algorithms, and of course the way that we perform the computations. So typically, you have a classical algorithm in the current thinking. You map this quantum algorithm in a quantum hardware. This mapping would require to load certain information on the qubits with operational gates, and then you execute an algorithm where you translate this algorithm into gates, arrange it in a specific way, and then you perform the measurement to retrieve back the information from quantum to classical. However, there are work in progress algorithms and some innovations that happen where they try to enable end-to-end quantum simulations. But then you need to know for sure the quantum systems that you are work on, so they are not still scalable. So you, for example, like the annealers, still you can have pretty much, you don't need to back again to classical. However, you need to pay attention to the type of problems you are working on and whether you can really do everything quantum or not. So it's still work in progress. There is some companies trying to leverage this for quantum sensing, for example, because it requires little operations to sense. But for large simulations, how you can map the kind of algorithms that we know about solving Hamiltonians or simulating molecules into an end-to-end quantum simulation. So this is still an open question. From time to time, a paper comes in with some development, but still those things are not up to the high scalability that we would expect from digital-based quantum computing.
Okay, thank you, Dr. Taha. A question from Yasser Moali. Sorry for the stupid question, but I'm new to quantum computing. Since a qubit can have an infinite number of states, why do we need multiple qubits? This is not a stupid question, by the way. It's good. And we are all new to quantum computing anyway.
Yeah, we are all learning about the field. So here we have to distinguish between the infinite number of states and the size of the system. So the infinite number of states would mean that the contribution or between the 0 and 1, because we have seen that the qubit can be partly in 0, partly in 1. This can vary. So you can have 10% in 0, 90% in 1. You can have 20% in 0, 80% in 1, and so on. Those are infinite if you represent them on a circle. However, when you do operations, it's not only about those coefficients. You need also to have what's called the computational space. And the computational space comes from many number of qubits, and that scales as 2 to power n, where n is the number of qubits. So if you have 2 qubits, it means that you can have 4 situations or 4 states. So you have the 2 qubits can be in 0, 0, can be in 0, 1, or 1, 0, or 1, 1. And this is the size of states that you are using for computation. So it is different from the coefficient. The coefficient, you can use them to store or load data, but the actual size that you are using to enable computation is comes in or scales with the number of qubits.
Thank you, Dr. Taha. Apparently, your talk was very interesting, got the attention of people, so we have still many more questions, but we don't have time. We got into the time of a session already without taking any break. I don't know if you prefer to take a few minutes of a break or just start the panel where people can maybe ask some of these questions in the panel discussion.
Yeah, definitely.
There are too many to finish before the next session.
Yeah. And we are gonna have many sessions coming. So tomorrow and in the last 3 days of the school, and those kind of questions will be answered during the school as well. They will come naturally in the materials.
Okay, great. Thank you, Dr. Taha. Very nice talk. Very thoughtful questions also. So should we move to the panel, or would you like to get 10 minutes break or something?
Whenever you like. Maybe we can get 5 minutes break, and then we're back to the panel, and then I can just announce the name of the panel in the chat so they prepare themselves.
Okay.
Yeah.
Okay. So we will start the panel in 5 minutes from now, where you can directly ask all your questions and get the experts to try to answer these questions. Okay, 5 minutes.
Yeah, thanks, Dr. Ahmed.